Okay, any questions before we start? Now, before I forget, on Friday there is no lecture. So the courses will be only until midday. So our afternoon lecture will not be. So you should, your homework is still due for Friday. I'm just expecting you to hand in your homework before 12. Just throw it under, give it either to me in my office or throw it under my office door. Any questions? Up to now we have been discussing the electric field, the potential, the energy. Okay, so this week we will be starting with conductors. Well, practically every application of electromagnetism involves some kind of a conductor. If you imagine any kind of circuit, so what we do in a circuit is basically just create some conducting network which guides the electric fields, magnetic, well, not much the magnetic field, mainly electric fields and the currents around, and eventually we have all our laptops and tablets that we use. So the conductors form an important basis of the applications of electromagnetism. Now, some simple properties of the conductors. Well, first, the definition of a conductor is a conductor is basically any object which contains charges that are free to move. It doesn't have to be metals, but if you have an object and if that object contains some charges that are free to move around inside that material, then we call it a conductor. Some examples are, for example, metals are conductor. In metals, we have all these electrons that are free to move around. Or salty water is a conductor because when you dissolve salt in water, you have the sodium and chlorine ions, which are charged. They are free to move around. And well, you even have, I don't know, let's say, you can even imagine some gases of plasma, for example. Plasma, you can just, it's a kind of a gas. It is a conductor where you have the electrons and the nuclei that are free to move. And in fact, if you have ever seen a lightning, the lightning basically travels through a plasma, so it just breaks down the atoms in the atmosphere into electrons and charged ions, which becomes a conductor, and the thunder just follows this conductor. Now, since there are charges to move around, and we are talking about statics, so this is an important, a key word in this discussion, that we will be dealing with statics. So there are charges that are free to move, but they don't move. Since they don't move, we know from Newton's mechanics that there shouldn't be any forces acting on them. If there are no forces acting on them, that means there are no electric fields. Because if you get a charge, put it in an electric field, then there will be some force acting on it, and if there is no other force, it will just start moving around. But in statics, that cannot be. So in statics, electric field is zero inside a conductor. Well, if you have zero, the divergence of zero is also zero. But we know that the divergence of the electric field is nothing but the charge density divided by epsilon 0. So no charges inside the conductor. Well, the underlined word is a key word here. The charge is zero inside the conductor, but nevertheless it can be non-zero on the surface. So if there cannot be any charges inside, whatever charge you put in a conductor should go to the surface. And this surface can be inside the conductor or outside the conductor. So it doesn't really have to be only outside. And let's see. This is an example of a conductor. If we put some positive charge over there, in that case, the positive charge will go to the surface. And there won't be any charge inside. If you have a conductor and a cavity inside the conductor, and you put some charge, and there is no charge in the cavity, then the electric field inside the cavity will also be zero. Now, one kind of confusing example might be, let's say we have a conductor. Inside we have a cavity of a, let's say, a special form. Let's say this is our conductor. And now you put some positive charge over here, some negative charge over there at a given time. Well, one might think that, okay, there is the positive charges and negative charges, they will attract each other, so that positive charge and that negative charge will stay there. So that seems to be a plausible argument, but it doesn't work. And the reason, to prove it mathematically, the easiest would be, let's say, if we had this configuration, then there would be such an electric field. At least one electric field line will have that form. And then we can imagine such a closed loop. And for that particular closed loop, E dot dl around this closed loop would not be equal to 0. Why? Because we know that the electric field here is always 0. There is no contribution from this region. But in this region, the electric field and the dl vector, they are both pointing in the same direction. So E dot dl is positive in this region. So you sum up, and that loop integral becomes non-zero. But we have seen that the curl of an electric field in electrostatics is always 0, and hence the loop integral of the electric field is always 0. So it cannot be. So there's a contradiction over there. So there cannot be such a electric field inside. So if there is an inner cavity, whatever the shape of the inner cavity is, whatever the initial charge distribution you create in your conductor, when the conductor reaches static equilibrium, electrostatics, that no charges no longer move, there cannot be any charge inside your conductor. Of course, the case where you have a cavity inside, and let's say you put some positive plus Q charge in that cavity, even in this case, you cannot have any charges inside your conductor. What will happen is, if you put some positive charge over here, it will attract the negative charges in the conductor. So the inner surface will be negatively charged. If your conductor is initially neutral, then you put some negative charges on the inside of the conductor. The remaining charge, the remaining positive charge, will go to the outer surface of the conductor. Well, it won't be necessarily uniformly distributed. It depends on the shape of your conductor, but nevertheless, it will be on the surface of the conductor, not inside. Now, how to see that in this example? Well, just take this Gauss surface. Over that Gauss surface, E dot ds. Well, the electric field inside the conductor in electrostatics should be 0. Electric field is 0. If E is 0, its integral is always 0. But this means the enclosed charge should be 0. Well, if the enclosed charge is 0, we also know how much charge is accumulated in the inside of our conductor. Q in the inner surface should be equal to minus Q. We know that they are already inside, and we also know how much charge is there. Just based on the fact that the electric field inside the bulk of the conductor should be 0, we can say that in the inner surface, the total charge should be 0.
In the previous figure, how don't positive charge and negative charge attract each other? Or don't they cancel out each other? So all of them are
They do attract each other. So let's say if this is a metal, there will be electrons that are free to move. The electrons here, well, the picture we usually have is the electrons here move to this place, neutralizing the positive charge.
And that's why you don't have to.
Yes. But of course, it's not really the electrons here that is going over there. You see, if you have a conductor, it is everywhere you have negative and positive charges, everywhere. Even at this point, we have negative and positive charges. But they are just on the average, we have equal amounts of negative and positive charges, so that point looks neutral. Here we have this point which is slightly which has slightly more negative charges than positive charges. But there are negative charges right over here. So if there are more negative charges over here, they will push this negative charge, which will push this negative charge, which will push this negative charge, etc. And eventually the negative charges over, well, the negative charge here will push the negative charge over here. So it will fill this this lack of negative charges at this point. So this point becomes neutral. So it's like there's an empty seat over here. I push her, she pushes him, and he pushes her. So eventually I fill her place, she fills his place, he fills her place, and she fills the empty place. It's not that I am going to that empty place. So that's why the idea that, okay, this negative charge attracts this negative charge, it really doesn't work, because we have all the charges nearby, which we have to also take into our discussion. And finally, if you have a conductor of any shape, which is, let's say, charged, well, inside there are no charges. All the charges on the surface, and those charges will be creating an electric field. So we have a positive charge, it will create some electric fields, and that electric field is always perpendicular to the surface. Electric field is always perpendicular to the surface of the conductor. And this is also, again, due to the same reason that there are no electric fields inside the conductor. Because if you imagine any metal, we say that, the charges are free to move inside the conductor, let's say in the metal in this case. Electrons are free to move in the metal, but they are not free to go out of the metal. So if they try to go out of the metal, there are some refraining electromagnetic forces that will force the electron to stay inside the metal. It's not allowed to go out. But if there is a horizontal component of the electric field, let's say at this point, if this was the shape of the electric field, then you say at this point, the electric field has a component parallel to the surface and perpendicular to the surface. Well, there are, as we said, there are forces preventing the charges to go out of the conductor. So perpendicular component will be balanced by these internal forces due to the metal. But the horizontal component of the electric field will create a force acting on the electron, pushing it to move inside the conductor parallel to the surface. There is nothing that would prevent that. So this motion is not possible, again, in electrostatics. We are only talking about electrostatics. When we have dynamics, none of these conclusions will be correct. But at least in electrostatics, the electric field on the surface is always perpendicular to the surface. This will be true even if you take a conductor, let's say a spherical conductor, neutral, you put it in a uniform electric field. So what will happen is this electric field will force the charges inside our conductor to move. Let's say this is a metal, the electrons, in which direction the electrons will move? To the left or to the right? To the right, to the left. So which direction will the electrons move in this electric field? Yeah, you see, initially, this is neutral, homogeneous, no charge anywhere. Then we put this in an electric field. At that moment, it's not electrostatics anymore. So the electrons will start moving until electrostatic equilibrium is reached. So which directions will the electrons move? So one left, one right, left, 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 left. You?
Right.
Right. So how can you convince him? Or how can you convince the others?
Since electric field goes from positive charge to negative charge, so if the left side of the conductor is positive and the right side of the conductor is negative, so it will be in the direction of electric field.
But you see, this electric field is created by some other charges somewhere else.
I know, but
So let's say we have positive charges over here and negative charges over here, which creates this electric field.
and the charges of the conductor should match this theory that electric field goes from positive charge to negative charge. I mean, if the electric field passes through the conductor, so
Does it pass through? Will it pass through? When we reach electrostatics, will it be able to pass through?
So it should be at the left.
The electric field is on the left side.
No. I mean, the electrons should be left side.
On the left. So you also think it's on the left. Okay. The electrons will come here. The positive charges will move, will remain on the other side. And this motion of the electrons will continue until, you see, there are two, when you try to evaluate the electric field at this point, there are two sources of the electric field which you have to superpose. One is all these charges creating this uniform electric field. On top of that, you have, when the charges in the conductor move, they will also create their own electric field. So since the external electric field is in this direction, the charges in the conductor should create an electric field in the opposite direction so this electric field inside the conductor is the sum of these two contributions, and eventually the accumulated charge will be strong enough so that its electric field will exactly cancel the external electric field, and we end up having zero electric field inside the conductor. But now, the electric field, let's say at an arbitrary point, will also receive two contributions, one from this external uniform electric field, plus there will be an electric field created by this charge distribution in the conductor. And it will be eventually the total electric field will have such a shape such that when it meets the this conductor, the surface, it will be perpendicular. Far away, it is still uniform. On the surface, it is perpendicular to the conductor we have. This will be the shape of the electric field lines. And of course, if you are sufficiently far away from the conductor, it will be slightly deformed and eventually become uniform. So this will be the electric field lines created by the by a uniform electric field. Now let's see, there is an external electric field that we are exerting. We have an external electric field, plus we have some charges over here on the surface, let's say, and some charges on the other side. Well, these electric field will exert forces on these charges. And so let's say we have these negative charges over here. There's an external applied uniform electric field. What will be the direction of this negative charges over here? The force acting on these negative charges. These negative charges will still feel a force. They are charges inside an electric field.
Şimdi bir tarafa doğru elektrik kuvvet olacak, bir de yüzeyde çarpınca sektirecek.
Now I'm only looking at the force due to this applied electric field. What will be the direction of the force acting on these surface negative charges due to this applied external uniform electric field? So it will be in this direction, towards the left. What about the forces acting on this side of my conductor? Towards the right. So we have this sphere. So both sides will be pushed in opposite directions. So if it is an elastic conductor, its shape will be deformed because this electric field is exerting basically a pressure on my conductor. So let's try to calculate that pressure. Now, pressure was basically, if you remember the definition, it is the force per unit area. Pressure might change from point to point. So what you do is you take the limit as the area goes to 0. You take a very small area. You calculate the force that is perpendicular to that area, the component of the force perpendicular to area, and divide by the area. What you obtain is the pressure. That's the definition. Now, the force is, in this case, it's due to the electric field. But we already know that on the surface of the conductor, the electric field is always perpendicular to the surface. So the force is perpendicular to the surface. So what is the force? You see, we have such a surface in an electric field. It doesn't have to be uniform. We have some electric field. And here in this region, we have an area A, and let's say the surface charge density is sigma. Now, what is the force acting on it? It's the electrostatic force. Q times E divided by A. What is Q in terms of A and sigma? Sigma times A. So it is sigma times E. Well, almost. What is this E? Which E should we use? We have a surface charge density. We know that the electric field is not continuous. So should we use the electric field that we obtain when we approach the surface from this side, or the electric field that we obtain when we approach it from the other side? In the case of conductors, it will make a significant difference because we know that inside the conductor, let's say this is inside the conductor, so if we approach that surface through this side, the electric field is 0. So the pressure we obtain would be 0, whereas if we approach it from the other side, it will seem non-zero. So which one to use? It was the average. Now let's see why. Okay, this will be the correct answer, but of course we need to have a justification. Why not take the electric field at both parts with different weights, but just equal weights? Why not use the electric field on one side or on the other side only, but take the average? We have to justify it. Now, we already have studied what happens to the electric field if we cross a surface charge density. So if you remember, we know that the electric field at the top minus the electric field at the bottom was equal to sigma over epsilon 0 in the n direction, where n is nothing but a unit vector pointing from the bottom of the surface to the top of the surface at the point that we are evaluating these electric fields. Now, the electric field at any point will basically have two contributions. The electric field created by, let's say, this area, the electric field at this point, let's say, it will have two contributions. One, the electric field created by that very small patch, plus the electric field created by all the other charges in my system. Now, for these other charges, if we only look at this electric field, this will be continuous through my patch, because for this electric field, there's no surface charge density at that point. This doesn't have any contribution from the surface charge density over there. No? Okay. So this is E other. What we call E other is this one. Let's take this shape. This is E other. E other is created by all these charges. There's a hole over there. Do you follow? But you see, the surface charge at this point is 0 for E other. Since the surface charge at this point is 0, E other is continuous through this point. It's not continuous through this point, but it is continuous through this point. It doesn't change whether you go to that point from this direction or from this direction. It is continuous. Now, the part that creates this discontinuity is the electric field created by the surface charge itself. But very close to the surface charge basically creates this electric field. Let's say on the top it is in the n direction. On the bottom it's in the minus n direction. So it's basically you have this very small patch. But if you are very, very close to this patch, almost on the surface of the patch is almost infinite compared to your distance from the patch, from the area. The patch is almost infinite. It is almost uniform, flat, infinite, flat plane. And we know that the electric field created by an infinite flat plane is in the normal direction, has a magnitude sigma over 2 epsilon 0, and it either points away or towards the plane depending on the sign of the charge density. So this is basically the component that changes discontinuously as you cross the surface. Now, but the force or the pressure that we had calculated, we said that it's sigma times E. An object cannot exert a force on itself. So the E that we have in the expression of the pressure, this E over here, is actually the electric field created by all the other charges. But E other is nothing but 1/2 the electric field at the top plus the electric field at the bottom. So because the electric field at the top has this EA with the plus sign, electric field at the bottom has the same EA with the minus sign. When I add them up, this EA, the electric field created by that very small patch, it just cancels. What remains is the electric field created by the other charges, which is the same for E top and for E bottom because that is continuous. So when I take that sum, the only thing that remains is the electric fields created by the other charges. So kind of we are done. So that's why we have to take on the surface, if we want to calculate the pressure, we have to take the average of the electric fields on both surfaces, not the electric field on one side or nor the electric field on the other side, but just their average. Now, for a conductor, and pointing out of the conductor, E bottom, the electric field at the bottom of the surface is 0. So electric field at the top is just sigma over epsilon 0 in the normal direction. So you see, electric field at the bottom is 0. So if you write this electric field for the bottom of the surface of the conductor, this should be 0. But that tells us that E other should be just minus EA. So we know what E other is. We already know what EA is. We have determined what E other should be. So E other is related with EA. Well, we can write the same expression for the top of the surface. For the top of the surface, EA will come with a plus sign. E other also has the same expression with the plus sign. They are equal to each other. And hence, at the top of the conductor, the electric field at the top is just sigma over epsilon 0 n. So the pressure, we can just write it as sigma over 2, let's say. It was sigma. E other is 1 over 2, the electric field at the top. Of course, its magnitude. This is equal to sigma squared over 2 epsilon 0 or 1 over 2 epsilon 0 E squared. No, you see, this is just one of the electric field lines. We have many electric field lines. It's just one of them.
Ya içinden geçiyor mu sonra?
Of course, I mean, even here, the electric field lines, we are assuming that it passes through the surface, not necessarily continuously. But what we had done is, this was our system. This was the system. So I divide it into two parts. This is equal to, we know the superposition principle. We talked about the superposition principle of the electric field. And so it basically states that if you have a system of charges, if you want to calculate the total electric field, just divide your charges, calculate in certain groups, you calculate the electric field created by each one of the groups separately, and then sum them up. So I made my grouping in this way. So this is my whole system. I just removed a very small portion on my patch. This is E. This is E other. All these charges, remaining charges, is creating E other. And then I put that part over here. It is this part, so I just delete everything else. This is the electric field created by the charges on the patch area A. Okay, so I have this system. I calculate the electric field created in this system, call it E other. And then I have this system. I can treat, superposition principle tells me that I can treat these both systems separately. So I can calculate the electric field created by this system only. And that is what I call EA. Now, if I look at this system over here, I have some surface over here, some surface charge. I know that the electric field, if I am crossing this surface charge, it need not be continuous. There can be some discontinuity, and the discontinuity in the electric field is proportional to the charge density at that point on the surface. Now, if I cross this point, this E other will change discontinuously. It will just jump from one value to the other value, and the difference in these values will be proportional to the charge density at that point. If I cross this point from one side to the other side, the electric field might still be discontinuous, and the discontinuity will be proportional to the charge density at this point. But since I removed all the charges at this point, the charge density at that point is 0. So E other is continuous at this point. Then I have this EA. There is a surface over here. If I cross the surface from one side to the other side, the electric field will be discontinuous, and the discontinuity will be proportional to the surface charge density here. But I can do more than that. I can also say what is the electric field just on the surface of this region. Well, I use many things here. I know that I have a conductor, so the electric field is the electric field lines are perpendicular. So that is one thing I implicitly use. And if I'm very, very close to this surface at the center, let's say, this area is very small, but I'm also very, very close to the surface right at the center, then it will just look as if it is an infinite flat homogeneously charged surface. I know the electric field of such a system. It has to be sigma over 2 epsilon 0 in both directions. So I know what EA is. I don't know what E other is, but I also don't care about what E other is. It is continuous. But I do care about E other if I'm trying to calculate the force acting on this area. Because the force acting on this area will be due to the electric field created by other charges, not by this one. So the force acting on this area element will be proportional to this E other. And E other, I can obtain it through E, the electric field, by just taking its average, because this EA just changes sign on both sides of my surface. Since EA just changes its sign on both sides of my surface, but E other does not, when I sum the electric fields on both sides of the surface, the contribution from EA, it cancels. The only contribution that remains is from E other. That was basically the idea.
Hocam bir yukarı çıksın. Şurada P böyle yazdı ya, böyle iki sonucu var. Bu enerji density değil miydi?
Yes, it is the energy density.
Basit bir iş.
What are the units of pressure and energy density? What's the unit of pressure? Newtons per meter squared. What is the unit of the energy density? That is energy per unit volume. So joules per meter cube. But joule is nothing but Newton meter divided by meter cube. So we have newtons per meter squared. They have the same units. At least unit-wise, there is no problem. The unit of pressure is the same as the unit of energy density. And the pressure, indeed, is equal to the energy density. There's another thing interesting. If you just look at this expression, nothing in this expression is a property of the conductor. There's no mention of conductor in this equation. So basically electric field, well, eventually we will see that electromagnetic field can exert pressure on anything, not necessarily on conductors.
Hocam, mesela hani klasik yani Newton fiziğini düşündüğümüzde hani ben bir yere basınç uygularsam sonuçta da bana yani bu kalemi normal force uyguluyor. Aynı şey burada da var mı o şekilde bir şey? Yani sonuçta hani bu elektrik alanı bir force uyguluyor ama
Well,
surface'inde olan
the concept of force on electric field is, I mean, you cannot define it in the sense of Newton. Because the concept of force in Newton is based on the concept of mass, whereas the electric field does not have a mass. The concept of force, you can say it is the change in momentum created by a force. Let's say if there's a change in momentum, then you can decide to call it a force. And we will see that electromagnetic fields carry momentum, and their momentum can change due to interaction with other materials. So you have a momentum change of the electromagnetic field, which you can, if you want, call it a force. But we will also see that the pressure of an electromagnetic radiation, there is a pressure if there is a magnetic field. I mean, this is not really a pressure of the electric field, but we know that it exerts a pressure on conductors.
Yani önce böyle basınç uygulandığında enerji mi veriliyor içinde?
Well, you see, pressure and force, they are quite related concepts. Energy and force, and pressure and force. So it's not such a big deal that the energy density turns out to be proportional to the pressure.
kondaktör olmayanlarda
There will be. We will see. I mean, when we study materials, electric fields in matter, which we will do in a couple of weeks, we will see that it exerts a pressure even on dielectrics. If I'm not wrong, the main difference will be instead of epsilon 0, that we will have epsilon. That is in linear dielectrics. Now, before you go for a break, let me also, and we will not study it in detail today, but let me just mention the uniqueness theorem. Now, the uniqueness theorem basically states that if we know the divergence of the electric field, the curl of the electric field, and boundary conditions, or let's say the Laplacian of the potential and boundary conditions on phi, basically they are equivalent, are known, E or the phi is unique. Not really, not much. Well, now I added this one, because in the next chapter we will be discussing the uniqueness of the solution of the Poisson's equation. Helmholtz theorem is this one. Now we will see that it's a strong claim that the solution is unique, because it just tells you that you can do whatever trick you want, as long as if you can somehow, you can cheat, you can do whatever you want, if you can somehow find a function that satisfies the Poisson's equation, and it also satisfies your boundary conditions, then it is the only solution. If you made some assumptions to find that solution, then you are not missing out any other possible solution, because there is no other possible solution. There is a single solution that satisfies both satisfies your equation and satisfies the boundary condition. So after this point, for a couple of weeks, we will just see the consequences by just make as much assumptions as you like, as long as you can, at the end, prove that what you obtain, your end result, satisfies your equations and satisfies your boundary condition. You don't need to worry about your assumptions. They have to be correct. They are no longer assumptions. Any last questions before you go for a break? No, I mean, we will discuss the uniqueness theorem later on. I mean, because I will be using this uniqueness theorem. That's why I just wanted to mention it. There's no proof. I mean, we will be discussing the proof later, probably tomorrow. Okay, so see you after 10 minutes.